We're going to talk about mixtures today. Mixtures can be divided into two categories, heterogeneous and homogeneous. Now, a mixture is when you have two or more substances that are combined together, but they are not chemically combined. So there's no set formula. In other words, water has a set formula, 2 H's with 1 O for every molecule of water. But if I were going to make sweet tea, each person has their own individual recipe for what sweet tea should be. There's no set formula for how many scoops of sugar you should have or how many bags of tea. Now, when you look at mixtures, you're going to ask yourself a simple question. Is it well mixed or is it poorly mixed? This prefix hetero means differently or different. So a poorly mixed mixture would be like raisins and peanuts. If someone served you a cup of raisins and peanuts and you don't like the raisins, you could pick out the peanuts that you wanted to eat and give the raisins to someone else and trade them for the peanuts that they don't like. Now, not all heterogeneous mixtures go into the next two categories, but these are subcategories for heterogeneous mixtures. So some heterogeneous mixtures will be suspensions, and some heterogeneous mixtures are colloids. Now, a colloid is a mixture that scatters light when light passes through it. And I have some examples here: milk, fog, and jello. Now, it may seem to you that the jello and the milk don't go together because the jello appears clear, but if you were to shine a light through the jello, it does actually bend the light. It's called the Tyndall effect, and it scatters the light in there. What gets tricky about colloids is that some of the particles are so small that we can't see them when we look at the solution. That's the reason it's important to test it with the light. Now, a suspension is something that has rather large particles that will settle out if you leave them alone to stand for a while, like vinaigrette dressing. Before you put it on your salad, you know that you need to shake it up and mix it well so that you get all those wonderful flavors on your salad. So we have suspension and colloids. One settles out after a time, and one scatters the light. Now, we come over here to homogeneous mixtures, and homogeneous mixture means well mixed. Now, that prefix homo does not mean the same. And I know in our culture you want to say that. But what homo means is similar. So when we look at homogeneous, well mixed, we're talking about two different substances that are mixed together so well that it's hard for you to tell the difference between them once they're together. So salt and sugar, if I were to mix those together in a bowl and then put those next to your cereal, you wouldn't know that there was salt in there until you tasted it. Pretty nasty joke. Now, solutions are a subcategory of homogeneous mixtures. And a solution is when light passes straight through. So when the light passes through the substance and doesn't have the Tyndall effect or the bending of that light wave, we know that we have a solution. Now, not all solutions are liquids, like tea here is a liquid. But we also have air and alloys that, like brass, that are metals in a metal solution. Now, it's important for us to remember that a solution can be a gas, a solid, or a liquid because air is a gas in a gas solution. We have gas solutes in our air that are dissolved into another gas. So let's talk about those components of a gas. We have two different parts of a gas, the solute and the solvent. Now, a lot of students struggle with keeping straight which one's which, so I have a couple of suggestions for you. First of all, the solute is what gets dissolved, and the solvent does the dissolving. The solute is the lesser amount. The solvent is the greater amount. Now, a nice little way to remember that is if you count the letters in the word solute and count the letters in the word solvent, you'll see that solvent has more letters than solute. So the longer word is the greater product. It's the part of the solution that is larger. Now, there can be more than one solute in a solution, but there can only be one solvent. And the state of the matter of the solutes, whether they're solid, liquid, or gas, does not matter for the solution. But the state of the solvent will determine the state of the solution. So let's look over here in my little picture. These blue little dots represent water molecules in my cup. And I have a Coca-Cola here because the red molecules are my syrup, and the green molecules are the caramel, and the black dots are my caffeine. Let's make the green dots the carbon dioxide because my Coke is not flat. So I have my syrup, and I have my carbon dioxide, and I have my caffeine in the water. So I have three solutes in here. The water is the solvent because I have more of those than I do anything else. The Coke that I drink is a liquid, just like the water in the Coke beverage. Now, the carbon dioxide is a gas, but it's dissolved into a liquid. So as long as my Coke doesn't go flat, in other words, get warm and have low pressure so that the gas can bubble out, I'm going to drink that gas within the liquid. The syrup is a liquid, and when it's dissolved into the other liquid, it remains a liquid. Okay? Now, when we're talking about solutions, we need to talk about solubility. And there are three different ways to describe the solubility or the saturation level of a solution. And we can say that they are either unsaturated, saturated, or supersaturated. Now, unsaturated does not mean that it does not have any solute. It just means that it does not have the maximum amount of solute for a given temperature. And saturated means that I have the maximum amount of solute for that temperature, and supersaturated means that I have more solute than I can hold. I like to compare this to eating breakfast. If you ate just an apple for breakfast, then you had breakfast, but you are unsaturated because you just had your fruit serving. Now, if you had breakfast at home, maybe you made some toast to go with your apple, then you might be saturated, especially if you drank some milk with that toast and that apple. Now, supersaturated is if you stopped by the Waffle House on the way to school and got one of their all-American meals and ate all of everything that was served to you, you would have more breakfast than you could hold, and you would be super saturated. Okay? Now, if you skipped a meal, you would also be unsaturated. So unsaturated does not just mean no solute, it means not the maximum amount, less than the maximum amount. Now, notice that all of these are related to temperature. So I have here a solubility graph that is comparing three different solutes. We have solute A, solute B, and solute C. Now, each of these solutes are being affected differently by increasing temperature. Solute C is going to decrease solubility as temperature goes up. Solute A increases temperature dramatically as temperature goes up. And solute B is not really affected by the change in temperature. So we have a solubility graph, and the purpose for the graph is to allow us to compare the three different solutes to each other. And notice that on the side, my label here says solute in grams per 100 gram of water. Always make sure you read the side labels for a graph. It will tell you what your measurements are in. Down here I have my temperature in degrees Celsius. Now, notice that we have three different points. And what a solubility graph will do a lot of times, it will ask you to compare the solubility of the different solutions at different temperatures. So for point 1, I have about 35 or 40 degrees Celsius at about 75 grams. And what the question might read is, if I had 75 grams at 40 degrees Celsius for solute A, how would you describe that solute? Well, that solution would be supersaturated because this point is above line A, supersaturated. It contains more than it can hold. Now, any point on a line is considered the line of saturation. So any point on that line is the saturation point. Anything above the line is supersaturation, and anything below the line is unsaturated. Now, be careful to compare the point to the correct line. So if I look at this dot right here, number 3, that's on solute B's line, to compare that point to B, the correct description would be saturated because it's on the line of saturation. But the correct way to describe that same point for solute C would be supersaturated because it is above line C. And then for line A, that point is below. So line number 3 would be unsaturated when compared to solute A. Now, something else will happen when you look at a solubility graph. They may ask you to compare the solubilities of two different solutes and find out when they have the same saturation level. So if you notice, point 2 is at the intersection of solute A and solute B. And so I could say that at this temperature, about 40 degrees Celsius, both solute A and solute B have the same amount of saturation. And so that would be about 35 grams per 100 grams of water. Now, something else that you can predict when you look at a solubility graph is when you see this downward slope, like see, you can predict the state of matter that solute is. Because we know that as a gas gets hotter, it will increase its volume, and that will be a bad thing if we're trying to put it into a liquid. If you think about your Coke, when your Coke gets warm, all those bubbles come out and your Coke goes flat. So as temperature increases for a gas, its solubility goes down. Okay? Temperature is not the only thing that can affect the solubility of a gas. So we have some different factors here: surface area, agitation, temperature, pressure, and concentration. And I want to compare these different factors for a solid in a liquid and a gas in a liquid. So surface area is like the crushing. I want to focus, when we talk about solid in a liquid, we're going to talk about making sweet tea. and gas in a liquid, we're going to talk about our Coca-Cola. Now, when I take a sugar cube and I put it into my tea, it's going to take longer for that cube of sugar to dissolve into my tea than if I took crushed crystals of sugar in a teaspoon and put them into the sugar, into the tea. So crushing the sugar or increasing the surface area will increase the solubility rate for a solid in a liquid. Now, you can't crush a gas, so there's no effect here, okay? It's not applicable. Now, agitation is a fancy word for shaken or stirred. And you know that if you're making sweet tea, you want to stir the sugar in. So agitation is a good thing for a solid in a liquid. But you also know that you do not want to open a shaken Coke. So agitation is a bad thing for a gas in a liquid. Temperature, as I heat the water to make my sweet tea, I will be able to put more sugar into the tea. But if I heat my Coke, the gas will come out of the solution. So my solubility will decrease for a gas. Now, pressure does not affect my solid in a liquid. Pressure doesn't make very much difference for solids, but it will make a big difference for the gas solute in a liquid. So the more pressure I apply, the more gas solute I can get into my liquid. That's the reason all of your Coke products are made under pressure. They're sealed so that all of that carbon dioxide the carbonation can stay in the drink. The concentration is just a simple, a fancy word for how much solute am I putting in. And obviously, if I put more sugar into my tea, I will get it sweeter faster. And if I add more carbon dioxide into my Coke, I will get more carbonation.